Hi, this is Shui and Yaren. Today we'll present our Capstone project, which is automated sense-making for online tasks, advised by Yongsung Kim and Nikki Couture. Before I introduce our project, let me share a short story of Emma, who is a CMU CS student. Every day she opens multiple tabs for multiple reasons. For example, to research papers, post a question on Piazza, or solve problems in LeetCode. However, at night, she realizes that she opened more than 30 tabs on her web browser, and she cannot close those because she's not sure about what tabs are open and why she opens certain tabs. Modern days, people open multiple tabs for multiple reasons, like Emma. They hesitate to close tabs because they want to use those tabs to remind themselves for the later work and want to resume resurfacing later. At last, they lose track of tabs that they have opened, and we call this problem as tab overload. So to solve such problem, Schema has been created. It is an extension for the Google Chrome browser, which offers a workspace.
Sorry, the slides are not changing.
Shall I just use the normal presentation then?
Yeah.
Okay, I can do that as well.
Yeah, now it's good.
Okay, so can I resume from here? Okay, yeah, so to resume, so Schema has been created to solve a problem such as tab overload. It is an extension for the Google Chrome browser, which offers a workspace where users can manually drag and drop multiple tabs that are open in one's internet browser into multiple tasks. However, current version of Schema requires users to manually group tabs into tasks. And according to our baseline paper, this is problematic because this process requires a lot of interaction and cognitive cost. So in our Capstone project, we are automating the tab grouping process for Schema users using ML models.
So to help enable this auto tab management capability, we proposed to create a tab to task pipeline that can group tabs into sensible tasks. So this pipeline adopts a document clustering method called supervised clustering. And this pipeline consists of 2 steps. So first of all, we want to encode the tabs in a way that distances can be computed. And we can use that distance for the second step, which is the clustering step. And for step 1, we explore 2 approaches in this project. The first approach is what we call a cross encoder, where we input a pair of tabs and output the likelihood of those tabs belonging to the same task. And this likelihood can later be used as similarity score for clustering. So this is basically the supervised clustering algorithm used in the original paper, where this algorithm was proposed for document clustering. However, in this project, we also came up with the variation to address some speed limitations of this first approach. So the second approach we will introduce involves training a single tab encoder in a CMS network. And then we're going to use the tab encodings directly for the clustering step. We will discuss these 2 approaches in details in later sections. But before we do that, I just want to highlight some major contributions of our work. So we trained and tested the models on Schema user data, which is something that Schema has never done before. And this gave them a lot of important insights into their user behavior. We also engineered new features for tab grouping. These features are very informative and can definitely be leveraged for future experiments. And last but not least, we introduced this new variation of the supervised document clustering method that can speed up the pipeline. Next. And before we jump to the experiments, this is an overview of the integrated system with our model deployed. So the Schema users will be interacting with the user interface, and the user interface will send back the Schema user data to the backend for storage. And the major functionalities of our model is to first extract raw data from Schema backend and transform them into the useful features. And then it's going to compute encodings based on these features. after we get the outputs from our encoder, then we're going to use that outputs to transform into a distance matrix and then perform clustering based on these computed distances. Next. So other than the functional requirements, there are two major non-functional requirements that we need to keep in mind while designing our pipeline and experiment. So the first one is performance. Since we want our model to have a near real-time inference time, this means that our pipeline should be as fast as possible. And the other major requirement is scalability. So this means for our pipeline design, a linear time complexity would be preferred to something like quadratic or exponential. And for our experimental design, we want to train a model that's global and can be generalized well to other new users, because we want to avoid retraining the model too frequently as new users start using schema. Next.
From now on, I'll explain about our experiment to automate the tab grouping using cross-encoder approach. So there are two objectives for our experiment. First is to determine whether two user-saved tabs are similar, and second, to group the tabs into sensible tasks. In cross-encoder approach, we trained a binary classifier and inputted a pair of tabs to learn the similarities of the two tabs. And we wanted to answer a question such as what features are useful for learning tab similarities and the speed of the pipeline. As a baseline for our experiment, we use a simple classifier that only exploits URL domain to group the tabs. So for this experiment, it consists of 3 steps, which are data preprocessing, feature engineering, and modeling. Data preprocessing step was further divided into 4 steps, and the first one was creation of pairwise table. The original data set that we had at first consists of 5 columns, which are user, task ID, task name, title, and URL. And since we wanted to consider all possible combinations of 2 tabs in a pair to compute the similarities between 2 tabs, we create a pairwise table, as you can see in the slide. So it consisted of 10 columns at the end. And the second step and third step of data preprocessing required quantitative and qualitative EDA of our data set. If you see the figure 1, you can see majority of the schema users have more than 1,000 pairs, or less than 1,000 pairs. And we wanted to prevent heavy schema users from dominating the data set that we are using, and we wanted to prevent them affecting the model performance. So we put an upper bound of 1,000 pairs from each user. Also, we defined hodgepodge bad tasks, which are basically bad quality data set. We define them as the tasks that include multiple irrelevant tabs. If you see in figure 2, most of the users have less than 20 tabs in a single task. And we defined a task that have more than 20 tabs as hodgepodge tasks. Also, we qualitatively looked into the data set and we found out that if the task is named as daily or reading list, it tended to include multiple miscellaneous tabs. So we removed such bad tasks from our data set. The last step of data preprocessing was balancing positive and negative labels through SMOT, because we had much more negative rows in our pairwise table. At last, we ended up having 462 users and 14,000 unique tabs in our dataset, and we split it, the dataset into train, valid, and test sets using the ratio in the slide. The next step of our pipeline was feature engineering. We wanted to measure similarities between 2 tabs, so we first used the 2 features that were suggested in our baseline paper, which are URL-based features and title embedding. We also newly generated features, which are named entity recognition, NER, to distinguish 2 tabs that have similar titles, and website category classification. So for the second feature, website category classification, we trained a model on 30 predetermined categories, and the model itself returned top 3 most relevant categories for each tab. So for our data set, we had 6 features in total, which are title embedding, URL dot card coefficient, URL edit distance, title embedding cosine similarity, NER, and website category. The last part of our pipeline was modeling, which consists of 2 steps. First was feed-forward linear binary classifier to learn the commonalities of tabs. And second was clustering, which clustered the tabs into groups using the similarity scores returned from step 1. We used multiple evaluation matrix. So for binary classification, we used accuracy, TPR, TNR, and AUC. For clustering, we use normalized mutual information, which is NMI, to see how similar the clusters are to the ground truth tables. So for binary classification experiments, we used multiple combinations of features. And the most remarkable outcome that we found from the result was that adding more features on our baseline actually contributed to increase the accuracy, and also adding URL related features to the feature set led to improve the TNR, and adding title related features on the feature set actually helped to improve the TPR. So we conclude that based on that observation that URL-based features are better at predicting negative cases, and title-based features are better at predicting positive cases. Also, another noticeable outcome was that feature set 5 actually returned the lowest accuracy, and we wanted to find the reason why. The only difference between feature set 4 and feature set 5 was title embedding. And from this observation, we think that the model itself is not good at picking up a raw feature such as title embedding. And we also think that the model already learned the information that title embedding could have provided from other features, like other process features such as NER and website category. So from this observation, we conclude that adding title embedding could have just added more extra noise to the model and misled the model. We also performed clustering on the binary classification results using feature set 4. And the reason why we used feature set 4 was because it had the least trade-off between TPR and TNR. We used average linkage, and when the decision threshold was 0.4, the clustering model returned the best performance. Since we wanted to run our pipeline on real time for the deployment, we also checked how long it takes to process the entire pipeline. And to process 100 pairs, it took about 46 seconds, which is kind of too long. So we came up with another pipeline using another new model structure, which will be explained by Shui.
Okay, so next we are going to look at the single tap encoder approach. Next. So this approach actually uses the exact same raw data, and it undergoes the exact same pre-processing step. The major difference here is that instead of inputting a pair of tabs, now we input a single tab to the encoder, and the encoder is going to return a fixed length vector for each tab as their tab encoding. And these vectors are then used directly to compute the clusters. Next. To obtain this encoder, we train it as a CMS network. So CMS networks are most famous for image recognition tasks, and they're very good at learning representations. But there are also some popular uses of CMS network in NLP tasks. So one popular example here is the sentence BERT. And this is the model architecture that the famous sentence transformer library used for training their sentence embedding models. So we borrow the idea here to train an embedding model for a tab or for a web page. And the whole idea of CMS network is to force the embeddings of two similar tabs to be closer by training two exact same way sharing networks. The way that the network learns this similarity is through something called contrastive loss. This loss penalizes a small distance when the two tabs are similar, and it penalizes a large distance when the two tabs are similar, and it penalizes a small distance when the two tabs are dissimilar. So at the inference time, we actually only need one of the networks to pass in a tab and obtain its output embedding vector. Next. On this page, we have an example for our input data at inference time. So this red table is a data schema that we use for this experiment. So the features we use are raw URLs, raw titles, and website categories. And we chose a subset based on the insights from our feature ablation study. And we actually also removed some features because they are pairwise features, which do not really suit the single tab nature. As you can probably already see, title embeddings and website categories are two features that we borrowed from our previous experiments, but URL embeddings are something that we created for this experiment. So we obtained these URL embeddings through fine-tuning a sentence transformer model, which itself is a CMS network, and the architecture diagram of the fine-tuning is shown on the right. So comparing the performance of this fine-tuned URL embedding model and the original pre-trained model, we can see that the fine-tuning actually helped improve the model accuracy. Next. And this is the result table for the single tab encoder trained with output dimensions, because we were interested in seeing what output size would give the best representation. We trained the model with different output sizes ranging from 2 to 128. Here, a size of 64 gives the lowest loss and the best NMI score. And we also checked whether the fine-tuning of the URL BERT model helped with the tab encoder training. Since in the previous slide, it has already improved that the fine-tuned URL encoder has better accuracy than the pre-trained model. It's not very surprising that on this slide, we see that the model trained with the fine-tuned URL embeddings actually has better performance. One thing to note is that the NMI of our best performing model in this experiment is slightly lower than the NMIs from the cross-encoder approach. And we think it might be because for the single tab encoder, we used very high dimensional raw features, but we only used linear layers to process those features. The linear layers worked well for the cross-encoder approach because most of the features back then were post-processed like distances, and they have like much lower dimensions to learn from. So something else we can potentially try in the future for this single tab encoder is to try different model architectures. For example, we can try to add a few CNN layers in the beginning to better learn the information in those raw embedding features. Next. This is the result table for the computational performance of this new pipeline. So you can see at the inference time for the feature engineering step, we still need to pre-process URL. We still need to generate title embeddings and extract website categories. The only difference here is that to extract the URL features, before it took 26 seconds to engineer features like added distance, Jacob coefficients, and to extract domains. Now it's only 0.2 seconds to do the URL embeddings. And then for the modeling part, encoding is 5 times faster than before, and clustering is almost 20 times faster. So we think this performance gain mostly comes from, first of all, there are fewer iterations to work on for the model because right now we're only passing in a single tab, which is in the order of n. But before we are inputting a pair of tabs, so that really results in a complexity of n squared. And then the second reason here is because this single tap encoding vectors work better with the clustering algorithm. We can leverage the building methods of these algorithms API call to compute the distance matrix. But before, for the cross-encoder outputs, we need to process and transform them into a distance matrix on our own. Okay, next. So as a summary of our experiments, recall that our task is to explore methods that group taps into tasks. And we explored two approaches. First one is with a cross-encoder, and we set up an experiment as a feature ablation study, where we learned that the URL features are very good at predicting negative cases, and the web content representations, this is something like a title, are better at predicting positive cases. So the upside of this approach is that it can leverage the post-processed pairwise features to improve model performance. But the downside is that because of these pairwise features, it really requires a quadratic complexity, and as a result is very slow and not very scalable. That's why we explored the second approach, which is clustering with a single tap encoder. So this approach can really achieve linear complexity and is very scalable. But the downside is that the model performance is not as good as the previous one. So some future direction can be to add more layers to explore the different model architectures in addition to the fully connected layers. And that would allow the model to work better with the high dimensional raw features. Next. So in this last section, we want to share some follow-up analysis based on the results we've seen. And we think these insights can lead to some interesting future work ideas. Next. So the first question we want to investigate here is what are those error cases, and how can we do better? Is there a way that we can make better features to help improve the accuracy? So while we were doing the error analysis, while we're manually examining these misclassified cases, we noticed that a decent amount of these misclassified cases were misclassified because these pages have unreliable titles, and unreliable in a way that these titles do not really reflect the true intent of the web page. And here we're showing an example. This is the false negative case. And you can see like both websites are about portable power stations, and a human being can definitely identify them as similar websites if you read through the website content. But the models really struggle to do that because the website on the left has a very vague title called Anchor. So if we can get a more comprehensive and a more accurate representation of this website, for example, next. For example, one thing that we can do is to extract additional information from the web page's HTML. Here we extracted a short summary from the page's meta description tag. So this tag is usually displayed as part of the search snippet in a search engine results page. And this tag is meant to give the user an idea of the page content and how it relates to their search query. So we leverage that, and you can see that the summary provides much richer information about this page. And both summaries mention the keyword portable power stations, which is something the titles fail to do. Next. So we wanted to see if this helps improve model performance, especially the true positive rate, because as we learned from our feature ablation study, the semantic features like titles contributed significantly to the TPR score. We ran a follow-up experiment, and we collected these website summaries. We retrained the model using the two feature sets we used previously, and we replaced the titles with website summaries in all stages of modeling. It turned out that the website summaries improved the TPR by a significant percent at a small cost of TNR. So this is like 6 to 10% jump. So this is very exciting. And this also means that it would be beneficial for a schema team to start collecting these summaries of websites as a complementary feature to titles. So researchers can leverage this much richer feature in the future for their experiments. Next. And the second question that we want to touch upon is how robust our model is to the hodgepodge tasks. Next. So as Gary mentioned, we dropped certain user tasks because they are considered like hodgepodge or bad tasks in our data pre-processing step. So these are the tasks where the user is kind of like grouped unrelated tabs or tabs from multiple areas of interests. And oftentimes users have these kind of tasks because either they needed a temporary workspace to host some tabs to review later, or they simply wanted to avoid the sorting and the taxonomy on tabs because it is a very costly process. So when we train the model, we wanted to drop these kinds of tasks because they would introduce too much noise. But as data scientists, we still want to examine the robustness of our model on these bad tasks and see how our model performance can be interpreted in such a noisy but closer to reality setting. Next. So we evaluated models trained with feature set 2 and feature set 4 on the hodgepodge tasks. And for both feature sets, the TPR drops by around 10% on bad tasks, while the TNR is able to keep at the same level, if not higher. So there is a drop on these hodgepodge tasks, and it is very much expected because if a task involves too many unrelated tabs, then the model would have a hard time finding similarities between those tabs. But a drop in TPR does not necessarily mean that our model certainly would fail on the mission. So we picked some hodgepodge tasks and clustering on these tasks, and we manually examined the clustering results. What we see is that even though the original task contains multiple unrelated tabs, our model is actually able to identify those like smaller groups of tabs that share like similar topics. So this is a very desired behavior, and this is exactly why we want to have these models around, because we wanted to help users better organize their personal spaces, especially when they do not want to do that by themselves because they really see such like tab classification as a very costly process. Next. So that concludes our whole experiment analysis section. And this is a future work slide where we're going to share some future work ideas based on the results analysis. So we think some improvements on our work can include improving data quality by reducing the number of hodgepodge tasks. So we can have more high quality data to train on. And this can be achieved by educating users on how to properly create tasks in schema and allowing users to tag tasks like reading list, to-do list, or review later list, the kind of the tasks that have the potential to be hodgepodge. And this will allow researchers in the future to better filter out those hodgepodge tasks. And we can also collect better features like website summaries, as we showed before. And some other feature ideas would include website link tracer and other time-related and user activity features. And last but not least, we can also experiment with different model architectures. And this is something that we did not have time to extensively explore in our project, but would be a very important future direction. So for the next steps, we think it will be beneficial to start doing some online tests and collect user feedback as the offline experiments that we had before do not necessarily reflect the true user preference. And also the data set we worked with is not particularly large, as we removed and filtered out quite a few bad quality data. And we think the schema team should also consider retraining the model when they have more users or when they have more high quality user data. So yeah, so that is the end of our presentation. And because of the time constraint, we included some slides from our design and requirement reports from last semester in the appendix. So you can go to the appendix for more information. And now we're open for questions.
All right, thanks very much, guys. Great job. hold on here. Let me get my comments. So you did a great job describing the problem. I think it's, you know, pretty common experience for all of us. You did a good job with your architecture diagrams. You did a very good job when you discussed your results and your performance breakdown. I felt like you really understood, you know, what you were presenting and did it in a very clear way. You gave good detail on how the model worked and what the features were, and then how you trained the model. And a really nice job on the residual error cases. So, you know, where you were showing us the, you know, the examples side by side. I thought that was really nice. It was really a well-organized presentation, and I think the way that you guys drilled down on the results and continued to improve, you know, was really nice. So the progression, you know, to the, you know, to the single model was sort of a nice development, I think, in your understanding. So I really don't have too many criticisms. I think the project was great. But what needs to be improved before your project can actually be used by real users? Why don't we just start? I mean, I guess it's kind of obvious that you'd want to be able to explicitly let them manage their own hodgepodge tasks. But beyond that, is there anything else? Do you think that it's fast enough now to be used in the real interface?
Yeah, I can start. So I think the approach, like the single tap encoder approach, really improved compared to the first approach. And just from the offline experiments, this is, I think the latency requirement from schema team was 5 seconds. So this is like definitely within 5 seconds.
Okay.
But I think another thing that we totally want to test and consider is for deployment. Because right now we're thinking about like deploying the model to a like central server, which is definitely gonna cause some network kind of like latency issue. So we did not really factor that into account while we're doing the experiments. But on the other hand, we can definitely like deploy our model to the edge where we can do the model, you know, prediction on users' website. So this is kind of like consideration that, and the design consideration, we still need to talk to the schema team about, right. Because the team does want to kind of like deploy our model and to at least on some users to see how fast it can do, and then what the performance and whether the user likes it. And this is right. Something that, like a bridge that we need to build before we actually deploy the model.
Yeah, it's almost like you'd have to have another whole capstone project on how to scale the deployment part of this to make it super fast for lots of users in parallel, right?
Yeah, for sure. Yeah, we haven't really touched upon on that because just for the experiments, there's a lot of like room to explore already. So yeah, but like we've already handed over our project to the schema team, and they have like a whole team of engineers there to talk us through the whole thing, and then maybe they will get like,
so,
you know.
So they're basically working now to try and put this into the real production version of the system.
Yeah, they actually already, I think like they have like a side project of classifying the tabs into existing projects, which is not exactly what we're trying to do here. We're trying to do like something more complicated, but they have started using some of our features, and they used our like training pipeline in GitHub. So they're still kind of like leveraging the work from us, even though they haven't got to the deployment side of our model.